When I run into the sword actor, I'm taking a certain lesser damage. I'm technically taking 80% of damage being used by the sword from the curve table. Notice how for a level of 2.5 for weapon hit effect, we must be applying minus 60 damage. But I've configured this weapon hit effect as a physical effect that will be negated by armor. So for my armor of 20, I will be taking 20% lesser damage to my health, that is minus 48. Similarly, configuring this to a magical effect means I will be reduced damage with magic resist. Magic resist being 10, I will be taking 90% damage, that is minus 54. So how did we achieve this? This is because of meta attributes. They are temporary attributes that are needed so frequently that they're made part of the attribute set itself. We can write the universal behavior of meta attributes, how they scale and apply damage to their corresponding attributes, based on incoming physical and magical damage and other parameters. This saves us from having to do such damage reduction or amplification in MMCs and CCs for all effects, and we can just write the common functionality in one place. Now every effect can simply apply damage through these meta attributes, and the functionality will perform the necessary operation each time, without needing special calculation classes for each and every effect. In the second part of this section, we'll be learning about custom calculation classes through two effects, Poison and Inferno. Poison shall apply periodic damage to all attributes, health, mana, and stamina. Notice in this Poison effect, I've configured a CEC which does attribute captures again, as with MMCs. I have written modifiers here, just like the effect modifiers above, for meta attributes. Even though they're all configured to do minus 10 damage for all base attributes, notice how I take lesser damage to mana and stamina. I have configured the CEC to take lesser damage if that attribute pool is less than 50%. And the next effect is Inferno Effect, which could be periodic infinite if you wish, and will apply increasing periodic damage for longer time the target is under that effect. This is the equation it follows: base damage plus n-1 times base damage plus 20%. As you can see, minus 10 first, then minus 11, then minus 17, and so on, for 4 seconds. And for the second application, it starts with minus 5 damage, although damage still increases each period. That's because we are using a temporary variable for the CEC. Apply minus 5 base damage if the current health is lesser than the threshold value. We shall begin with meta attributes in the first section. For some fast-changing, crucial, and frequently updating attributes like health, mana, and stamina, it would be beneficial to have certain temporary attributes. The intent is to have such temporary attributes update the corresponding attribute values instead. Go ahead and open your base attribute set class, the header and C++ file. If you have been following along, they must be stored in Ability System Attributes folder. I have meta attributes for all three base attributes, health, mana, and stamina. As developers, meta attributes gives us more control of these temporary attributes, like reduce or amplify their values based on certain effect and other conditions, preventing us from modifying attributes directly. So this is my health meta, which is also of the type gameplay attribute data, as with every other attribute. Although it has attribute accessor methods too, the only difference from other attributes is a lack of rep notify method. Yes indeed, if you can tell from the get lifetime replicated props method, we're not replicating this attribute to all clients. This value will be used by the server only, and any calculations will be done only in the server. So far, if you have been following along, you should have also declared meta attributes for mana and stamina, and you should have declared these three methods: the constructor, just to initialize base attribute values, get lifetime replicated props to indicate and configure rep notify conditions for the base attributes, and pre-attribute change method. The pre-attribute change method is used just to keep final new value of health or mana or stamina within its bounds, between 0 and their maximums. So as the name suggests, this method is called just before setting the attribute with a new value. So you can perform this last final operation to your attributes and set that new value by reference. For example, most games don't have health, mana, or stamina operating as float numbers, but rather as integer numbers. So in pre-attribute change, You could do the floor or ceiling of float numbers to keep integral attribute values. If you may have guessed, yes, we do even have the post attribute change method that executes after the pre-attribute change and the attribute value set. And unwrapping the pre and post attribute change methods, we have a couple more pre and post methods pertaining to effects. Let's go to the definition of the attribute set class, and in its header file, you can find these pre and post gameplay effect execute methods. Just read through what they suggest. They provide a single effect modifier data that is operating on the attribute. Yes, indeed, these methods execute only by effects, but not infinite or temporary effects that modify only the current value. If you remember, attributes' current values reset to their base values after the non-periodic duration or infinite effects are removed. So to read by the chronology of operations, let's declare the pre-gameplay effect execute before pre-attribute change and the post-gameplay effect execute after. Let's define both these methods in the C++ class, and it is optional to call the superclass method. You don't really have to do it. In the pre-gameplay effect execute, the very first of the 4 operations, I wish to further refine the incoming damage using the meta attribute. I want to take damage reduced by armor and magic resistance as in Dota 2, and probably in the future take an amplified damage based on the elemental effectiveness, like I take more fire damage if I'm a grass type character. Let's quickly have a glimpse at the effect mod callback data. It packages the effect spec, where it comes from, something called evaluated data, and the target AC of this effect. Evaluated data is technically the current single attribute modifier of the effect, which contains the modifying attribute, modifier operation, and the magnitude of the modification as you configured in your effect class. Let's attempt to get the attribute from the data's evaluated data and check to see if it is equal to our health meta attribute. And by my game design, let's use the same functionality to other meta attributes as well. So I will just use an OR operator for stamina and mana meta attributes. So this is what I intend to do. Reduce damage by armor or magic resist by checking if the effect spec is of type physical or magical damage, as in Dota 2. Now, let's attempt to get the armor from the owning AC. Yes, you could have also used the target property in the effect mod callback data, and we shall use this method to get the current value of armor getNumeric attribute. It accepts an attribute as an input parameter. How do we pass in an attribute when our attributes are not identified by tags or strings? Notice how it is asking for the attribute object itself. Let's first declare the battle attribute set header file, which is where the armor is stored, and from the battle attribute set class, we can use the scope resolution operator to call static methods and use the armor's getter attribute accessor method. That's how you send attributes where you need them in Unreal Engine C++ with GAS, since attributes are not identified by strings or tags. I wish they were. This returns the attribute and not its value. Likewise, we can get the magic resist value from the getNumeric attribute method of the owning AC and pass in the magic resist attribute using its getter static attribute accessor method. Now we are going to use something called asset tags to identify the type of damage the effect brings in, physical or magical gameplay tags. These are actually the asset tags of the effect spec that can be obtained from the incoming effect data. The effect spec has a method called getAllAssetTags that takes in a tag container by reference as a parameter and appends to this tag container the asset tags of the effect spec. Let's check to see if this asset tag container has the exact tag and it accepts a gameplay tag. Gameplay tags are used in C++ by calling the static getter method of the fGameplayTag struct requestGameplayTag. So Unreal Engine attempts to get this tag from a certain config file that it writes the tags of your project into. It does accept a parameter fName, which in Unreal Engine C++ has been modernized to accept a string of your tag name. The other optional parameter is just used to throw an error if the tag was not found, which you can just simply ignore. And now, since this data is being passed by reference, we can just set the new values to it. That is, from the evaluated data, we can update the magnitude. The operation will be factoring this magnitude with the allowed damage of the armor attribute as a percentage. So for example, if I have an armor of 20%, I can easily have them initialized when this attribute set is constructed. I shall actually be taking 80% damage. Likewise, we can check to see if the asset tags contains magical damage type. And please do remember, I have actually defined and imported these tags into the editor. If you haven't, you will get a runtime or compile time error. So for magical damage type, we shall factor in the evaluated data's magnitude with the allowed magic resistance percentage. Of course, we will not process any other damage type, like pure damage, as in Dota 2, and simply return a boolean true to fulfill this method's operation. The post gameplay effect execute method would be the best place to perform final operations. It is indeed the final D operation of the attribute modify. This is where we'll make the meta attribute apply the damage or heal to its corresponding attribute. So like we did in the pre-gameplay effect execute method, we will check to see if the evaluated data's attribute is health meta, and if it is, we shall set health using the setter attribute accessor method that accepts a float value. We shall use set rather than applying another effect spec to modify health with health meta, and the expression I will use inside is current health value added with current health meta, which should have already been set before the previous C method post attribute change for the health meta. Yes indeed, you could have also used the evaluated data's value instead. Just reread the code of this topic and you will understand how attribute interactions work in GAS. And finally, we can also reset health meta to 0. This is optional because you will keep overriding health meta anyway going forward. Now, what if the addition results in a higher health value than max health of the character, or resulting in a negative health value? Like for example, with a max health of 300, the addition goes up to 320, or for health of 10, I take 30 damage, resulting in minus 20 health. Do we need to do the fmath clamping here as well? Thing is, we actually don't. The reason being, these setter methods call the pre and post attribute change methods, the B and C methods of the attribute modification, and not the pre and post gameplay effect execute methods. This means the set health method will undergo further operation by the pre-attribute change, and since the clamping is done here, the health value's new value is always within the bounds of 0 and the max health. Similarly, we can do the same for mana meta attribute, simply setting the mana value with the current mana plus the current mana meta values. And likewise, for the stamina meta attribute, setting stamina by adding both attributes and resetting the stamina meta. This is all we need to do to set an attribute value with their meta attribute values. So that's all there is to it really. You can now build and compile your code and run the editor in debug mode. In my level, let's attempt to test the health meta attribute with this sword actor, which is stored in the matter weapons sword folder. Open up the sword actor class. This sword actor has a weapon collision capsule volume, and the capsule volume has been set to generate overlap events. We have implemented the onBegin overlap event, which applies a weapon hit gameplay effect to the target actor it overlaps. This weapon hit effect is stored in the ability system effects folder, which is actually an instant effect, and we have been adding to the health all along a negative value and the sword curve from a curve table that we implemented in the last topic. Going forward, we can just modify the health meta attribute, overriding it with the outgoing damage of any weapon or damaging actor in the level. The outgoing damage at level 2.5 will be minus 60. That will be the health meta. Now, I also wish to have damage types in my game, like physical, magical, pure, and effects can actually bear more features and metadata to it, like what type of effect it is. How do we add such data to an effect to describe and identify it? We can add more components to this effect. They're not actor components, but more functionalities that plug into your effect. Choose asset tags, and we can add tags to this effect class. Inherited means this effect could have been made a child of another class. For example, there is a sword effect parent class and a magical sword effect child class. Could be added a magical damage type gameplay tag and have the physical damage type gameplay tag removed from the inherited tags from its parent sword class. So go ahead and choose damage type physical gameplay tag. Now this is what our effect does. It gets minus 60 value from the curve table and overrides it with your health meta attribute. When the effect is modifying the target's health meta attribute, it undergoes the 4 operations we just learned, the A, B, C, D operations of attribute modification. The phase A is the pre-gameplay effect execute, where the health meta is refined with armor attribute and effect type. Then the B and C pre and post attribute change methods, within which we haven't written any logic for operating on health meta. The health meta operating on health is written in the D phase of the post gameplay effect execute method, which does the setting of the health attribute. And this in turn calls the B and C phases of the health attribute, the pre and post attribute change methods. In the pre attribute change method of the health, we've just clamped health value within the bounds of 0 and the maximum health. Yes, if you were building your own ability system, you would have probably done the same thing. You would have had pre and post operations before and after changing values, even with effects, to give developers more control over attribute modifications. So with the armor of 20% in the battle attribute set, we should be taking in 80% of incoming damage. And in my level, yes indeed, I took 80% of 60, that is 48 damage. Let me change this effect damage type to magical. I should technically be taken in 90% magical damage for a 10% magic resist. And yes, I did take 54 damage from the sword actor. Yes, I know, it doesn't really make sense, by design, to have a meta attribute. Imagine if I were in a game as a character, why would I make incoming damage as part of my system, a property or an attribute, right? But developers tend to find shortcuts. If there are fast-changing, crucial, and frequently updating properties like health, mana, and stamina, developers do find it inconsistent to keep updating that by mathematical operations all the time. Add this, subtract that. So a temporary variable could be kept in place that can do the damaging at all times, and the damaging instigator can just set or override these temporary attribute values instead. Yeah, developers can think in unconventional ways like that, as long as it helps them give more control and isolate functionality. So no more adding values directly to health, mana, stamina all the time. All your effects read better, just override metas with damage values. This completes the section on meta attributes. Just keep reading through the codebase and other completed projects to understand a system better. The next section is about custom execution calculation classes, CECs. Gameplay effect execution calculations are like the sibling classes of MMCs, in the sense that you can capture attributes and optionally snapshot them for complex calculations. Although, unlike MMCs, they give more power and control in modifying the effect spec that could involve changing multiple attribute modifications. The key aspect of CECs is that they are not networked and only run in the server and not on the client, and hence they don't support prediction in the client. They must also be implemented in C++. In terms of snapshotting attributes during their captures, it does follow the same lifecycle as in MMCs. Snapshotting of source attributes is done when the spec is created by it, and snapshotting of the target happens when it is first applied. Obviously, no snapshotting means always working with the source and target attributes' current running values on a per application basis. So, we can do 3 major things with custom execution calculation classes. Firstly, we can get values from the effect spec that were set by caller tags. Yes, you could set values for an effect spec using caller tags and blueprints, and these values can be obtained from effect specs inside CECs. The next useful functionality is the ability to capture attributes and snapshot them, just like MMCs. But it allows you to do little more operations over these attribute captures. Like attribute modifiers, you can add, multiply, or override these attribute values at the time of capturing and receive that calculated value for that attribute. So this gives you a little more control over adjusting attribute captures with some hard-coded values specific to an effect, like adding 50 over current health value or whatever. You can use this method, attempt calculate captured attribute magnitude, which takes in 3 parameters: the attribute capture definition, evaluation parameters of the effect spec, and the outgoing flow damage as an input parameter, just as in MMCs. And the third really great functionality CEC support is temporary variables, or in core C++ terms, transient aggregators. They are closely and tightly associated to gameplay tags, just like setting values using caller tags. So you need not always have to deal with attributes. Some values can be used by the effect for special calculations, and temporary variables can be used to achieve that. And they use gameplay tags like setByCaller tags to take in values. In this example, they've used a temporary variable associated with the data.damage tag, a quite universal and common tag for a project if you ask me. And they've performed a small modification to that, added the value of 50. Now this calculated value can be obtained in your CECs, and it doesn't even have to do anything with any attribute. You can use this property to add your temporary variables by tags, valid transient aggregator identifiers, and it is synonymous to relevant attributes to capture, to register your capture definitions, which you will use in CECs as well. So this valid transient aggregator identifier is a list of temporary variables identified by gameplay tags, just like caller tags. And you can get values from this list using an equivalent attempt calculate transient aggregator magnitude method, where you pass in the gameplay tag as the first parameter, followed by evaluation parameters and the outgoing float value. This is a flashcard I've made for custom execution calculations of gameplay effects. They're used for custom calculations for an effect. They have one function to implement, the execute implementation. It provides to developers more flexibility over the entire effect. It usually sends an output modifier for the effect spec. The drawback to this flexibility is that there is no networking involved. It only runs on the server, which also means there is no client-side prediction since it doesn't happen on the client. Meaning, for example, if your client is doing fast actions in a multiplayer game, they cannot have these values calculated on their end client side, and they always have to wait for the server to give them the final calculated values. Effect execution classes also support attribute capture definitions with or without snapshotting, just like MMCs. Beyond that, they also support something known as transient aggregators or temporary variables, which help capture certain special magnitude values for that effect, and they are closely associated with gameplay tags. So yeah, these are the three great functionalities of CEC: getting values using temporary variables identified by gameplay tags, getting values by capturing and snapshotting attributes, and getting setByCaller tag values. So in my level, I have this poison area actor, and I want to do a custom calculation to this poison effect. Go ahead and open up the poison area actor in your base, matter, volume of effect folder. This is what my poison area looks like. Yes, I haven't added any particular effects for the visuals. Go ahead and add your own material or particle system. The box collision component is set to generate overlapping events with overlap all dynamic collision preset. For the on component begin overlap event, I have copied the same functionality of the electric field actor, where overlapping actors are validated against an array of actors, and if they aren't contained in the list, add them and apply the effect. Notice how it still bears the electric field effect and code. I am simply applying a gameplay effect to the overlapping actors ASC, gameplay effect poison, stored in the base ability system effects folder. This is made to be a duration and periodic effect that applies grass.poison elemental tag. I did create this new tag for this topic. Poison is made to be a sub-element of grass. Go ahead and use your own creative ways to make more magical elements in your game, going by your world building and narrative design. Back in our effect class, notice how we don't have any effect modifiers, but we can have an array of effect execution classes. Each element of this array accepts an execution calculation class and calculation modifiers. Let me just clear this custom execution class and demonstrate CECs, since they must be implemented in C++. Click on the Tools menu above and search for the execution class. You will notice that if you clear the filter, execution class is indeed the sibling class of the modifier magnitude class. Go ahead and choose execution class, provide a name for your custom execution calculation class, prepending it with CEC, and use a new path for the effect execution classes. So for a public class type, the resulting path will be public ability system effect execution. So after you create this class, open up your IDE and you will notice you just have an empty class. Let's explore the parent execution class, and you will notice it does have its unique property, valid transient aggregator identifiers. If you scroll down, you'll find this blueprint native event, execute, that you will have to implement, just like the MMCs. No, CECs don't really have good blueprint support, despite there being a blueprint native event. And you must have learned by now, you can override and implement blueprint functions and native events in C++ by suffixing with _implementation. Unreal Engine generates something called generated header file for each class as part of the reflection system. And if you examine this header file and search for _implementation, you will find the same execute _implementation function, which is a C++ counterpart of the blueprint event of function. Notice how it is declared as virtual, meaning this is the C++ function you can virtually override in your children's C++ classes. So go ahead and copy this function declaration. For now, let's omit the virtual keyword. And back in your CEC Poison class, let's first start with the properties instead of a public access specifier, just to make things less complicated. I will declare a new gameplay effect attribute capture definition, poison, damage, health. Likewise, I will also declare attribute capture definitions for mana and stamina, since by my game design, poison shall deal almost equal damage to all three attributes. I want to do a certain calculation. I want to take in reduced poison damage if the target has less than half the value in that attribute pool. That is, less than half of health, mana or stamina pool, the target takes half the poison damage for that attribute. So this will mean we have to capture even current and max attributes of health, mana and stamina. As it goes with MMCs and CECs, we need to implement logic in the constructor where you have to register the relevant attributes to capture, and finally paste the function declaration of the execute _implementation that you must implement in CECs. You must use the override keyword in C++ to override parent class functions, and it's also a good habit to extend this class's functionalities to children classes, so I will be declaring this function as virtual as well. Within the constructor, let's begin to define the attribute captures first. But before we do that, let's quickly examine the gameplay effect attribute capture definition to get a recap of what we saw in the last topic. Notice how it has only three properties: attribute to capture, the source or target of the attribute, and if we should snapshot the attribute or not. And this has a convenience constructor allowing us to pass in all three values for this structure to use. Let's use that constructor to assign values to our declared poison, damage, health. For the first parameter, we pass in the attribute using the attribute accessor method of the attribute set class it belongs to. Don't forget to include the attribute set class header file in the C++ file. The second parameter is attribute capture source, for which we will use the value target. And we can snapshot this value since we want a constant stable value for the health meta. But in all due honesty, we won't be using this capture definition at all. It's just to show you how optional it is, even if it reflects in your editor. So it's a good practice to define these relevant attributes to capture, but we will really need the current health value of the target, for which we will not be snapshotting since we need its current running value in each periodic application. Likewise, do this for mana and stamina current values, no snapshotting, and capture their corresponding max attributes. Let's do it with snapshotting. Our game hasn't yet evolved to dynamically change max base attributes. And finally, the most crucial step in the constructor, add them to the relevant attributes to capture list to register them with this class for any effect. Yes, this relevant attributes to capture list is boilerplate and important. Don't forget to include it. So why in the constructor and why relevant attributes to capture? This is because when the editor runs, such classes are actually constructed, and these attribute capture definitions are created and registered as relevant attributes to capture. Yes, editor constructs these classes and can now visualize and render these constructed objects from your class in the UI. If you don't add these relevant attributes to capture, the editor won't construct and render the attribute captures that you need. So when you build and compile your code, and preferably run your editor in debug mode, and if you select the CEC poison in the list of effect classes, notice how you have calculation modifiers now, and the first element takes in the default value, first attribute in the list, poison, damage, health. So you can work with execution class values the way you did with attribute modifiers. That is, just like in modifiers property of the effect, how you modified the health meta by overriding with the damage value, you can override the health meta here with a new damage value. Click on the plus button here to add a new element to capture. Notice how you have 9 attribute capture definitions here? Yes indeed. This was the work of the relevant attributes to capture list. as you did in the constructor, reiterating on that. So now, your editor has constructed the CEC class, and your editor knows the relevant attributes to capture. So we'll just go ahead and add mana of -8 damage and stamina meta of -6 damage. Now I'm just going to leave this right here as it is without modifying other attribute captures. That is, if I attempt to add another element, I can choose to modify the current health captured attribute before execution. But if I don't want any modification to the current health to capture, I can remove this and leave this as it is. And the current health and other attributes will still be captured as they were configured to do so. Let's find out soon. This brings us to the execution using the captured and optionally modified attributes. Go ahead and define the execute implementation method. The definitions in C++ won't bear the virtual and override keyword. So what this function signature includes is an input parameter containing the relevant parameters needed for execution and an outgoing parameter that will be the final modifier for that effect. Let's examine this custom execution parameters. Jumping to the definition takes you to the gameplay effect execution class itself. This execution parameter bundles within itself essential properties required for your custom execution calculations, like the captured attribute definitions and their modified aggregators, transient aggregators or temporary variables, which you will learn about in the next section, the current effect spec, target AC, and so on. The second parameter is of the type custom execution output. Notice how you have a T array of modifier evaluated data. This output modifiers is nothing but the modifiers you sent to your effect spec, which we have learned is nothing but the attribute modification evaluation data, a certain modifier operation applied with a certain magnitude onto an attribute. So the goal in execute implementation of CECs is to modify this execution output by packaging a new list of attribute modifiers. We can get the spec to query a lot of information from the effect, which can be obtained from the input execution params using getOwningSpec method. Let's just match the function's return value. And if you remember, we needed the evaluation parameters for this method. We should declare evaluation parameters and optionally adding more data to this, like passing in source tags from the effect spec's captured source tags. It being a tag container aggregator, we can get the tag container with this method, getAggregatedTags. And likewise, set its target tags with the spec's captured target tags. So consider all of this to be our first and single step. Now the second step of this function's implementation would be to get the values that we need. Using this method, attempt calculate captured attribute magnitude, and so let's just do that. Weirdly enough, it is part of the execution parameters. I wish it were an inherent method of this execution class. Go ahead and call this method attempt calculate captured attribute magnitude. So, execution params are not too hard to understand. Imagine a bunch of properties and helper methods you need, and they're already bundled in this one struct, and that is pre-configured with all the relevant data and methods you need. The first parameter it requires is the attribute capture definition. Let's do poison damage health first, then simply pass in the evaluation params that we just made, and finally the outgoing float value that we need. Similarly, let's attempt to get the calculated value for the attribute poison damage mana and for poison damage stamina. Likewise, you can now easily attempt to get the calculated values for the other attributes as well, health, mana, stamina, and their maximums. The third step is to perform the calculation. Yes, it took us this far to get here. There were C++ rules we had to follow, but when you know them, it's really rewarding. Like you wouldn't even care, and you can implement features a lot faster. As part of my game design, I wish to be taking lesser poison damage if the ratio of these attribute pools are less than half, so we can validate that in this Boolean operation. If the ratio of health to max health is less than 0.5, I will set the value of poison damage value health we just obtained by half, dividing it by 2. I shall do the same validation for the mana pool and set the mana damage value by half, and likewise the same operation for stamina. This does mean I will be taking a damage of -5, -4, -3 for health, mana, and stamina if I have less than half of that pool, which we will see shortly. And that brings us to the fourth and the last step of the implementation, modifying the output execution output parameter, which in all honesty just requires adding new outgoing modifiers for attributes for that effect spec. From the out execution output, we can call the add output modifier method that requires gameplay mod evaluation data struct, which we have seen time and again is the attribute modifier data containing the operation and magnitude for an attribute. We are going to use this convenience constructor that takes in all three values in the parameters. So for this constructor, the first parameter we shall pass as the attribute object obtained from the attribute set class using its attribute accessor method. The next parameter we need to send will be the modifier operation, for which we shall override the health meter with the damage value passed as the third value. So it reads just like in the effect class. Make an attribute modifier and add it to a list of modifiers contained in the execution output. Repeat the pattern for mana meter and stamina meter using their poison damage values, and this literally completes the method implementation. Now let's build, compile and run the editor for the effect damage of 10, 8 and 6 for health, mana and stamina in my level. Notice I take damage of -3 and -4 for stamina and mana, that is half, for each periodic application, whereas for health, I took a damage of -10. And second time around, I took 10 damage to health on the first application, but 5 after. So in 5 applications, the first being 10, the other 4 being 5 damage, I took damage to 30 to health, resulting in 120. So the poison is doing half the damage when have the health, mana or stamina of less than half its pool. And here is a flashcard for the effect execution calculation classes, just to get a quick recap of it. And now we arrive at the final section, where we attempt to apply more periodic damage for an Inferno or a Molotov burn effect. In your base folder's Ability System Effects folder, create a new Gameplay Effect class named Gameplay Effect Molotov or Gameplay Effect Inferno if you would like. The intent is to have more periodic burn damage for longer duration under this effect. Quite similar to Molotovs in most first-person games, run through the fire and you're barely taking damage, or like in Clash Royale, the Inferno Dragon, which applies more periodic damage under its Inferno effect, and pretty much takes down a tar in less than 3 seconds. Now, let's make a duration periodic effect, of course, that applies a tag. Nope, not fire, but a fire Inferno tag. So just like this grass poison, I think it would be best to create a unique tag to this fire element and import it into the project. So these are the sub-elements of the magical elements in my game: Tornado for air, Ice for water, Inferno for fire, Metal for earth. Yes, initially I had thought of making electricity a sub-element of air, but I'm not the best at world building or narrative design. Go ahead and write the tags that work best for you. And in your base model folder, open up the relevant data table and click on the re-import button to bring in those new tags. Back in the effect class, you will notice more sub-tags to air, water, fire, earth. Go ahead and choose Inferno under the fire tag. Go ahead and create a new C++ class of the execution calculation class type, and inside the public folder of the ability system and effect executions. And in this CEC Inferno C++ execution class, we're going to implement temporary variables or transient aggregators. This allows you to go beyond attributes and do custom calculations using special values that your effects needs to operate with. For example, if you need to check if health is below a threshold value, this value need not even be another attribute. Like for example, Axe's Quelling Blade ultimate ability that pretty much deletes a target if their health is below a certain value, and such values can also be obtained as scalable floats from a curve table. So these variables are closely associated with gameplay tags, just like setByCaller tags, and these variables must be registered as part of your CEC construction with tags, just like relevant attributes to capture. And just like its attributes captures counterpart, we have the attempt calculate transient aggregator magnitude method to get the value of the temporary variable. As I had mentioned, I wish to check if target health is below a threshold value. So firstly, let's declare the health attribute capture definition, and then let's attempt to declare the transient aggregator by identifying gameplay tag but as a tag name. Because in Unreal Engine C++, tags are queried using a string of the fname Unreal Engine primitive data type. So for this temporary variable, I shall use a tag element.fire.inferno. Let's declare and define the constructor within which let's specify the health attribute capture definition. Attribute to capture being base attribute set's health attribute. Let's complete the other couple of properties of this attribute capture definition, attribute source being target and snapshotting to false, better to validate on running value of health. Let's not forget to add the relevant attributes to capture, passing in only attribute capture definition for health, and let's work with temporary variable or transient aggregator. Nothing much to do here, but just register your transient aggregator of the CEC class. Just like relevant attributes to capture, we have valid transient aggregators identifier, which is a list of tags for each of your temporary variable. Call its method addTag that accepts a gameplay tag, which in C++ is obtained using the fGameplayTags static method requestGameplayTag, and passing it the name of your tag, which you declared as a property of the CEC class. Yes, this is Unreal Engine C++ way of getting tags. C++ code queries the engine if such a tag is registered for that project. Don't worry, once you know the rules, it's going to stick with you. It's going to feel like muscle memory. For the sake of demonstration, I want to show the lack of existence of this tag. What does it look like for this CEC class? It will build and compile successfully, but it will give you a runtime error. Check this out. The runtime threw an exception in this line of code because these Unreal classes are constructed when the editor runs, and the runtime has attempted to get a non-existent tag. If you open the debug console and read the last line, it says the requested gameplay tag element fire inferno test was not found. Tags must be loaded from config or registered as a native tag. Yes indeed, Unreal Engine actually writes your tag into a certain config file, and you could register the tags there by writing there manually. But Unreal Engine is kind enough to excuse that and allow the execution of the editor. Please do remember to run in debug mode with this target or scheme editor development. In your Molotov or Inferno Effect class, you will notice there is only your health attribute capture definition and not your temporary variable. This is because that tag doesn't exist and Unreal Engine just ignored that temporary variable for the CEC. This could also happen if you fail to add this tag to your valid transient aggregator identifiers. So close your editor, correct the tag name to element fire inferno, and run the editor from your IDE. And in your effect class, you will notice the existence of the temporary variable for the CEC. For a demonstration, let's observe the captured health value after the addition of 50 and add the next value, temporary variable element fire inferno, which will be overridden by a certain value. So we wish to see if our health value is less than the threshold value as part of our custom calculation. We're just adding 50 to health to observe how our attribute capture is calculated and obtained. Of course, for the execution calculation, we need to override the execute method suffixed with the underscore implementation in C++ since it is a blueprint native event. And in the definition, we shall declare all float values we need, define the transient aggregator tag we're working with, and even get the effect spec. This time around, just like that, for demonstration, let me get the effect spec as a pointer, which means if this getOwningSpec method doesn't return a pointer, we must get its address instead by using this ampersand or reference operator before. It's not too hard, it just reads like this, address of this value, like a mathematical function, f of x. Train your brain in thinking in C++ ways, and you will not regret it. And finally, since the return value is a constant, your variable must also be a constant. C++ rules at play again. Let's get this tag from the effect spec, and since we're dealing with a pointer, we have to use the arrow operator to get values from the effect spec pointer. And so, from the effect spec, we can get the stack count using this method, getStackCount. Of course, we need to declare the evaluation parameters for our attempt calculate magnitude methods for attribute captures and temporary variables, adding in the source tags and the target tags from the effect spec tag aggregators for source and target. The step 2 of this method is to get the float values from the attribute captures and transient aggregators. So in the attempt calculate attribute capture magnitude method, we will pass in the attribute capture definition and evaluation parameters to get the health value. Now, as specified in the documentation, we will attempt calculate transient aggregator magnitude by passing the gameplay tag we obtained above and complete the function requirements, passing in the evaluation params and the threshold health outgoing value. And now, we finally reach the calculation step. This is the formula I wish to do. Damage equals base damage plus stacked value. The small operation I wish to do for base damage is to check if current running health is greater than the threshold value. If it is, I will do 10 damage, else 5. The percentage increase of 20% is going to be a multiplication of base damage with 1.2, and finally the stacked value will be n-1 times the percentage increase damage. So this will mean on first application, stack is 1, meaning this value will be 0. The modifier evaluated data is then written for health damage modification with the constructor. The first argument it needs is the attribute, which will be the base attribute set's health meter, followed by the modifier operation override and the damage magnitude. Of course, the damage has to be negated. Don't forget to do that. We have configured this magnitude to add to health, if you remember. And finally, in the execution output, we need to add the output modifier, the health damage modifier, and now you can build, compile, and run the editor. So in the Molotov or Inferno gameplay effect class, let's simply add to health a value of 50 to get the feedback and see the calculated captured magnitude. And let's also set the Inferno magnitude to 250. So now, for our health starting off at 200, we will get this value of 250, and that will be compared to the threshold value of 250, meaning it is not greater than the threshold health value, and we should be taking a base damage of 5. So let's add a breakpoint in our editor, which in most IDEs is in this left margin called gutter. When a breakpoint is added in your IDE and the program is made to run in debug mode, the program pauses execution when the program control flow reaches this breakpoint, allowing us to examine the values at the time of execution. Let's also make sure to set the effect class of the fire area actor to Molotov or Inferno gameplay effect. Now in my level, when I run into this fire area actor, I hit this breakpoint in my IDE. That means the program has paused execution, and we can examine the values of various entities in our code for the scope of this class. Please do remember, we do need to run the Unreal Engine editor in the editor development target or scheme of build and execution to pause at breakpoint in your IDE. This here is actually this object the breakpoint is in, that is, the CEC Inferno. Notice how you can actually see the values of the properties of this object. Health here is the local variable float value used for the attribute capture definition. Notice how you have 250 even though you had a value of 200 of health in your level? Yes, the addition of 50 for your health attribute has actually happened as part of the effect CEC execution modifiers. The debugger has been placed in the last line, which means your code has also constructed the outgoing health damage modifier. Hovering over this, you can examine this variable. Notice how the damage is negative of 5, the base damage. Going by the formula, for the first application, the stack is 1, meaning we're not adding any stacked value, and the threshold value being 250, our health is not greater, which means the outgoing base damage is 5. Notice how we have a value of the transient aggregator tag as well, the right tag. If I hit play, after a second, the breakpoint is set again during the second periodic execution. This time, notice how health has a value of 245, haven't taken that damage of -5. The stack still remains 1, that means the outgoing damage magnitude will continue to be -5. That is, the percentage increase in damage by the stacked value resulted in 0. So removing this breakpoint and continuing the execution, we will lose 25 damage over a duration of 4 seconds under this effect. So now it begs the question, how do we increase the stack? Reapplying an effect spec is one way. It will involve creating and applying a new effect spec, but GAS allows manually incrementing or modifying stack count, which will be much more efficient and performant. That will involve modifying the effect spec in C++, which is not actually allowed by this const read-only return value we get. There must be another way to modify the effect spec we get from the execution params. That can be done using the getOwningSpec for pre-execute mod method, part of the execution params. So this returns a non-const pointer to the effect spec. A non-const return value allows us to change the value we get, meaning we can update the properties of the returning effect spec, but we should be careful with modification of the effect specs, and it shouldn't hurt to just change stack values for certain effect specs. In C++, a const after the method declaration means this method is a constant method, meaning it cannot modify any internal property of this object inside the function's definition or implementation. Whereas const preceding the function declaration means the return value is marked as constant, meaning the return value is assigned only to another constant variable and it cannot be modified or reassigned. So to give you a simpler example for a better understanding, Let me try with JavaScript. For example, when you declare a method as const, you cannot set its internal properties with new values within that function's definition, like how this function is unable to assign new values to a and b of this class test. Whereas when you declare the return value as const, you cannot reassign or set new values for its internal properties or even call certain non-const methods. Coming back to our implementation, we can get the gameplay effect spec pointer called mutable effect spec, and from the execution parameters, use the getOwningSpec for pre-execute mod method that returns the non-constant pointer to the effect spec. That was exactly why in the first demonstration of the CEC Inferno, I used a pointer by referencing that const effect spec, since I would be using a pointer eventually. So Unreal devs usually return a pointer for values that can be modified, and const lock the real object when returned by reference. Observe the header file to the left, and you will notice this pattern all the time. Const is followed by ampersand reference operator, and pointers are non-const and mutable. Now, replace the effect spec with mutable effect spec variable. The pointer access format will remain the same. As I had already mentioned, Gas allows manually incrementing or modifying stack count, and we should do just that on each periodic application by using the mutable effect spec and calling its setStackCount method that accepts a new integer to set, and we shall just add 1 or pre-increment the stack variable we have. Let's now add a debugger in this new last line we have for this implementation, and let me run into this fire area actor. Yes, we hit the breakpoint during execution. We can examine the variable and objects at this point. Yes, I did add 51 to health in the effect spec, which means we are above the threshold value of 250. This means our health meta will take in the damage of -10 in the outgoing attribute modifier. If we run the execution once again, we will hit the breakpoint again, and we got a different value for health, 241. This means -10 damage through health meta did apply to our health attribute. We do see a value of 190 under the element fire inferno gameplay tag bearing effect, and in the second run, the stack count is 2, for which the outgoing damage modifier magnitude is -11. It was the additional 20% value we added to the base damage based on the stack count factor of 2 minus 1. So base damage of 10 plus 2 minus 1 times base damage of 10 times 1.2 for the 20% increase in damage. Likewise, for the third run, we have taken a damage of 11, the stack count is 3, and we do have the same formula. This time, since 241 is less than the threshold value of 250, we get the base damage of -5. We get -17 as the outgoing damage modifier, and as I keep pressing the play button, notice how the magnitude is increasing as the stack count increases. And yes, as we calculated, we end up with the health of 110, and if I run into this actor once again, we get the added value of health as 161, magnitude of -5 since health of 161 is less than the threshold value of 250, and keep observing the increasing health modifier for each stack. Yes, at stack 3, it becomes -17, and so after the 5th application and a damage of -29, you'll end up with a health of 25. So yeah, that's all there is to it. Backtrack the steps to understand the structure and the implementation even better. And this brings me to the end of this topic, in fact, the end of the Gameplay Ability System series. Yes, I know, it took me more than a year to complete. Sometimes, I feel like I shouldn't have started off with this ambitious project. It felt like running a race that I already lost, but I had to still finish the race. I had to finish what I started. And so, I did make sure to bring about chapters 5 and 6 after a long break due to a job change and other responsibilities. If you made it this far, I thank you from the bottom of my heart for making it till the end of this journey. This journey has taught me so much, and I'm sure I've brought value to many people with these lessons. I really hope you can use these lessons into your own craft and building a great upcoming game. Thank you once again for being part of this long journey. Feel free to clone my project from the GitHub repository or download for free using the Gumroad link provided below. It would mean so much if you consider donating if this project helped you in any way possible. And hoping to see you in a new Unreal Engine video in the future. Until then, never stop fighting.